All right, hello again, invisible students, and welcome to the first module of the third unit of the course. So at this point, you've gotten 2 exams under your belt. We've been introduced to 2 different hypothesis tests. As I've said throughout these little video chats we've had, the hypothesis testing procedure is going to be the focus from here on out. So we're going to begin the third unit by talking about another set of hypothesis tests. But first, we will do a little bit of review on where we've been. So again, remember that we're pretty transparent about what's on tests here. Every test from here on out, you are going to be asked to decide what test is appropriate for a data set that's described to you, a study that's described to you. The reason why, again, is that computers can do all the actual math for us. They can't decide which test to run, at least not yet. For now, you got to know which tests are appropriate for which situation. So that is heavily, heavily emphasized. So last test, you only had 2 different rules to follow, 2 different choices. Again, they both were what were called one-sample tests. We had one sample of actual data compared to a population that we knew some stuff about. If we knew that standard deviation of the population, we ran a z-test. If we didn't know it, we ran a single sample t-test. Today, we talk about something we alluded to in the last module, which is situations, very common in research, where we have 2 samples of scores gathered by the researcher that we want to compare to each other. Essentially, we don't know anything about either population that is present in our hypothesis tests. So in both the z-test and the single sample t-test, we knew some of those key parameters about our populations, but oftentimes in research we don't do this. Again, the classic experimental condition versus control condition. It's a situation where we don't claim to know anything about either population, so we want samples to represent each. There's a couple different ways we could approach this. Let's say, for example, that we were interested in measuring kids' reading comprehension at a school. We want to try to make them better readers. There's a couple different ways that we could create 2 samples of scores that would let us make that comparison. First, we could take the same group of kids. We could measure them before we do anything at all, and then give them a new reading technique that we hope is going to improve their comprehension, then measure again afterwards. The second one, we could take a group of children, split them into 2 roughly equal groups, give one group a new technique that measures reading comprehension, or it tends to increase it, and the second group an established technique, and then measure both of them after some set of time has happened. If you remember your methodology, you can see we're pretty clearly describing first a within samples design, within participants design, and second, a between participants design. That's our next key decision rule for our 2-sample t-tests. So 2-sample t-tests are run when we have 2 samples of scores that we want to compare to each other. We don't know anything about either population. Which 2-sample t-test you run depends on whether you use a between participants or a within participants design. So let's start with the most common approach. Between participants designs are the most common type of design for reasons that we'll get into a little bit later. But again, remember, between participants, 2 totally different sets of scores. There are different people in each condition. You're randomly assigned to one condition or the other. Like a child either learning to read with an established technique, that's our control group, or a new technique, that's our experimental group. So again, other examples, maybe we want to measure aggressive behavior as a function of heat. We split participants up. They're either in a hot room or a ordinary temperature room. We measure their aggressive behavior. Maybe we want to measure media effects. We randomly assign participants to either watch a funny movie clip or a depressing clip, then we measure their mood. Again, no participant is in both conditions. Every participant is in exactly one, and they're randomly assigned. That's what makes it between participants. So here, the test we would be running, and it's right on the top, is a t-test for independent samples. And I apologize for my lousy handwriting. I'll spruce that up before the next video. So again, here's how the t-test for independent samples works. First, when we use it, 2 samples of scores, both gathered by the researcher and compared to each other, like an experimental and control condition. It's a between participants design where each participant is randomly assigned to exactly one condition. So here's how it works. The procedure is not much different from our t-test for single samples. The biggest difference here is that we now have nothing but sample data. There is nothing that we know about either population. We don't know any mu's, we don't know any sigmas, we don't know any of that stuff. We have nothing but sample data to estimate those population parameters. So again, the key question we're asking is the difference between the sample means that we see, instead of between one sample mean and a population mean that we're comparing it to, is the difference between the two sample means that we've got, is it so large, is it of such a size that it's very unlikely to be due to chance? The answer is yes, and again, our threshold is what our alpha level is. The answer is yes, that's awfully unlikely. We conclude the samples come from populations with different means, which generally means we're going to be rejecting the null. So, does mu1 equal mu2 is still the classic question of the null hypothesis. It doesn't really change, but now both mu's are being represented by sample means. So here's the only real big snag that happens here. Other than that we have to calculate an extra mean and use that as a stand-in for mu, the single biggest problem is how do we calculate the variance of the population? Remember, that was the big problem with the single sample t-test. We calculated the variance of the population by using our sample data, and then we converted that to a standard error, and it became the denominator of our test statistic. Here we're going to do that again, but now we have 2 samples worth of data. And remember, more data is better. You want an accurate an estimate of that population parameter as you can get. So we want to use all of our data, and it would be a little arbitrary to just pick one of those samples and use that as our sole estimate. The best way to do that is to combine them together. So we can calculate what's called pooled variance. Pooled variance is just combined variance. It's just as variance that we calculate using data from 2 samples, or more, but in this class it'll only be 2. So we basically start off the same way we do for ordinary variance calculations. We use the sample sum of squares. We use the degrees of freedom for each to calculate pooled variance. So remember, sums of squares formulas, we've seen these before. Those have been the numerator to our variance formulas. Hasn't changed. We'd be doing this separately for each sample. Then what we do is we calculate what's called pooled variance. Notice this is the symbol for sample variance with a little p, which of course stands for pooled. We take the sum of squares from our first sample, we add it together with the sum of squares from our second sample. That's our numerator. Our denominator is the degrees of freedom from our first sample plus the degrees of freedom from our second, added together. Then we divide. Now some of you are doing the PEMDAS thing and are saying, wait, didn't you just add before you divided? We can't divide until we have a full numerator and a full denominator. So we have to solve that numerator and denominator before we can divide. Sometimes I see students mess this up and they like split this formula in half and do each one separately. Don't do that. It'll give you the wrong answer. Add up the sums of squares, add up the degrees of freedom, divide. Again, the reason why that makes sense with PEMDAS is because you have to have an actual numerator and denominator before you can divide. So that's what you're solving for first. Okay, so that would give us our pooled variance, a estimate of population variance based on the data from both samples. Now what do we do with it? We never really stop with a variance, right? We convert it to a standard deviation and then a standard error. So that's what we do here. Again, the formula looks a little bit different, but it's not hard to calculate. First things first, notice that our standard deviation here, or standard error, excuse me, has m1 minus m2. That's not a real equation that you're plugging numbers into. That just indicates that it is the standard error of the difference between those 2 sample means. So don't try to solve this. You don't need to. You never need to solve anything on the left side of the equals. But over here, notice we're going to plug in our pooled variance twice and divide it once by the number of people in the first sample, divide it again by the number of people in the second sample, then add those together. And notice that that dividing line is split. That's why, again, that's why you now divide and then add. So we add those 2 things together, then we take the square root, and that gives us our standard error. So different formulas, but you'll have them in front of you, and they're not hard to calculate at all. The key thing, again, is those sum of squares. They're coming back. They're becoming much more important. We haven't seen too much of them in a little while. So calculating sums of squares separately and remembering that the degrees of freedom is the number of people in each sample minus 1. We'll see some examples in future videos. But this is our first point of emphasis. The single biggest change in shifting from a single sample t-test to an independent samples t-test is accounting for variance from both samples. We calculate this pooled variance. We don't have to worry about this with related samples t-tests, which are done when we have a within participants design. We'll talk about that in a couple videos down the line. They don't have this problem. You don't have to worry about accounting for the different people in our different samples. The reason why? Give it a little bit of thought. We will pick up on that when we talk in a couple of lectures about the related samples t-test. But first, we're going to run through an example of a hypothesis test with this new independent samples t-test approach. See you there.